One of the things that was really not satisfying was taking a biology class and seeing the Krebs cycle represented by blob A goes into blob B and you get blob C. And so being the curious person that I am, I wanted to know what those blobs were, and it turns out it was chemistry. And so I've always kind of been trying to understand, why does this happen? Why does this happen? And chemistry was that kind of nice middle ground where it's not so abstract, but it's still like enough detail that felt satisfying to me. I'm Marilú Pérez, or Marilú Pérez, and I am a scientist at Ames National Lab. I do research, and I have a group that does computational chemistry. It sort of depends. A lot of the times we are trying to understand what's happening with a particular experiment. Oftentimes you run an experiment in the laboratory and you see some interesting behavior or some results, and there's not always an easy way to access what's happening on the atomic scale. But luckily, physicists and chemists have developed models, have developed the math that governs how the different molecules and atoms move. So we can put a molecule into a software, try to find how they interact. Usually it's based on their energies, and try to give some insight into why you're observing what you're observing. And a lot of times, and one of the big goals is to predict what's going to happen if someone puts different chemicals puts them together in a lab setting, what they will expect to see. And that's kind of the holy grail. That's kind of what we want to be able to do, is know enough of the physics, know enough of the math behind how the molecules move around, and get it in enough detail to predict what one would see in real life. Separations are everywhere, but in particular, I've been focusing on separating rare earth elements. And rare earth elements all behave very similarly and are often found together in mixtures. So a lot of the science that we're trying to do is kind of like picking out all of the green M&Ms in a jar of M&Ms without knowing really, or being able to physically touch and know that we are doing it. So we need to design the experiments, we design the chemistry around it so that you can pick out those green M&Ms from the rest of them. But more than that, it'd be ideal if we could separate all of the colors in one go, for example. And so the reason why rare earth elements are important and why we care to put so much effort into that is that small amounts of particular rare earth elements, like say the green M&M of the elements, just a little tiny bit gives materials kind of superpowers. For example, dysprosium is found in rare earth magnets, and it makes them stay magnetic at very high temperatures. And so that means it can be used in a lot of different applications, and where the magnets are exposed to a lot of harsh conditions. And so that's why it's important that we be able to access those materials so we can, or those elements so we can make those materials. I mentioned magnets, and the reason magnets are really important is because a lot of the newer technology that we are developing for clean energy applications, EVs, more efficient consumer electronics, they're going to require magnets and electric motors. And to be able to transition away completely from fossil fuels and still maintain, a comfortable lifestyle that we're used to, we're going to need to have new materials that can really push us into that next wave of technology.